Now we're going to take a look for a moment at a situation that happens surprisingly often. What if I have two figures, a larger outside one and a smaller inside one, and I want to find the area in between them? Now when I say this happens surprisingly often, let me give you a few examples. Something that is kind of easy to visualize, or at least it is for me, out of this is imagine that the large gray square is like a piece of property, like your yard. And this white square represents a pool that's just been installed. Hey, good for you, huh? So you had all of this yard space, and the area would describe how much yard you had. And now we need to know how much yard is left after we take out all that space for the pool. So the question is, what is the area of this gray spot where we've taken out this square? Another example would be a picture in a picture frame. If we want to know the area of the picture frame, say we're going to stain it or something, and we need to know exactly how much wood stain we need to change the color of the picture frame, we would need to know that area, and so we would want to find that edge around. Doing some types of tiling, like in construction kind of stuff where you put a tile on a wall, this comes up sometimes. How much area do we need to cover once we take out this piece right here? And so here's how we do it. It is easiest to common sense the way this works by thinking about this. The whole thing is the area of the gray section. And so I'll say a gray. That's the whole area. And then I'm taking away from it, that is subtracting the area of the white square. And so all I have to do is calculate the area of the gray one, calculate the area of the white one, and then subtract. Now the thing that makes this difficult is, of course, I've given this to you as polynomials. So in order to find the area of these are both parallelograms, so I would use base times height. So I'll actually have to calculate those areas up and then subtract those polynomials. So it basically sums up everything we've done in Module 5. So let's start by finding the area of the gray section, including the spot that would be underneath the y square, or the white square. That's going to be base times height. So in this case, base and height, these are perpendicular. I can use whichever one I want. So I'm going to say 3x minus 4 times 9x plus 2. And now I'm going to distribute this, and for space sake, I'm going to kind of do this quickly. You will want to write this out fully as multiple instances of the distributive property, or you can use your box method, whichever one you prefer. But when I do, I'm going to get 27x squared plus 6x minus 36x minus 8. And I can combine my middle terms, and so I get 27x squared minus 30x minus 8 as the area of the gray polynomial. For the area of the white one, I promise that's the word white. It's still base times height, but in this case it's going to be x times 2x minus 1. That's just the distributive property, and so the area of the white one is 2x squared minus 2. Now that I have those, all I have to do is subtract them. So I take the area of the gray one, 27x squared minus 30x minus 8, and now I'm doing polynomial subtraction, so I'm going to put that in parentheses so I know to think of it as one polynomial, minus 2x squared minus 2. And I'm just looking for common terms there and there, so 27x squared minus 2x squared would be 25x squared. There is no linear term, there's no just x term over here, so the minus 30x stays the same. And then my constant terms, I have a negative 8 and a negative 2, but I'm subtracting them. Negative 8 minus negative 2 is negative 6. And so this expression right here represents the area between those two figures. And so that's how you're going to do that. There's just a couple problems on this. Mostly this is a way to make you practice both multiplication and addition and subtraction all in the same type of problem. But it's also a good exercise in thinking of the kind of areas where you're going to see this. All right, good luck.